Okay, good morning. I think last time we have talked about the polymers, particularly in the introduction of the polymers. And in this chapter, we start to talk about how we can make the polymers. Okay? The polymerization is different from any organic reaction. Okay? Polymerization is different from organic reaction because of the high molecular weight of your final product, which is called the macromolecules or polymer. Okay? And it starts from your monomer. During the polymerization, you will obtain the high molecular weight product. That's the difference between any organic reaction versus the high molecular weight polymerization reaction. So the polymerization is different from low molecular weight organic reactions. So in that case, we have to talk about the degree of polymerization, because how many molecules of your repeating units in the monomer to form your polymer is different from the organic reaction. Right? So we have to know about how many residue, how many repeating units, how many the degrees of polymerization in your polymer is quite different to determine your molecular weight. Okay? We will talk about later how we can measure the molecular weight of your final product, but let's talk about the polymerization. Okay? Now, the question is, what kind of polymerizations do you know? Can you name any polymerization reaction that you know? Stepwise? Step growth polymerization? Wow. Okay. What else? What's the opposite term for the step growth? Step growth and addition polymerization? Okay. Well, if you talk about the step growth, then I think you should know about the chain growth polymerization reactions. Chain growth. Okay? I will show you what's the difference between the step growth and chain growth. But you know, as its name says, step growth is the reaction where you go like a step. Okay? Whereas a chain growth is like a ring, or the chains gathering together. So if you have many monomers in your reactor, the chain growth polymerization will go from one monomer to the other monomer like a chain, whereas the step growth polymerization is going from any sites. So you have increased molecular weight very slowly in the case of step growth polymerization, whereas in the chain growth polymerization, because of the like a chain reaction, the molecular weight is pretty high at the beginning in the case of chain growth polymerization. So we will talk about that. Anyway, there's a difference between step growth and chain growth. You talked about the addition polymerization reactions. Okay, addition, that's good. What's the opposite side of the addition? Condensation. Okay, addition reaction and the condensation reactions. Is there any difference between addition condensation versus the step growth and chain growth? Addition reaction is the same as chain growth polymerization? Or condensation is the same as step growth? Will be my question, okay? If you know all of my questions, then we don't need to. We will very quickly go through this chapter 2, but if you do not, then I think we can spend some time how I can describe this addition versus the condensation reactions. Okay, that's the subject of this chapter 2. Okay? So we will find whether addition polymerization is the same as step growth or chain growth, and vice versa. Okay? So in next slide, I have elaborated a little bit about the types of polymerization reactions. Addition. Addition means you add your monomer to become a polymer. Okay, so you add. Condensation means that you have, of course, you will get a high molecular weight polymer later on, but you have a condensate. Condensate. Condensate means byproduct coming from the polymerization reactions. Whereas in the case of addition polymerization reaction, you do not have any condensates. If you have a byproduct, we call that as a condensation. If you do not have any byproduct, we call it as addition reactions, no matter what the mechanism of your polymerization reaction is. So this is the method of classification of your polymerization reactions depending upon whether you have any byproducts. Okay? So for example, polyesterification reactions. Esterification reaction is coming from the diol alcohol reacting with carboxylic acid, right? Your byproduct is water. If you have any, during those esterification reaction, if you have a byproduct, we call this reaction as condensation reactions, okay? In the other example is that we have a styrene monomer, styrene. You have a vinyl group and a benzene ring and as a substituent groups. Okay, vinyl group opens your double bonds and add to become a high molecular weight polystyrene. In that reaction, you do not have any byproduct because of the opening of a double bond, which is radical or electrons gather together to become a covalent bonds. In that case, we do not have any condensation, condensate or byproduct, so we call that as addition reactions. Okay? Ring opening means, as this word says, you start from your monomer with a ring, just like a caprolactam. Caprolactam or caprolactone has cyclic ester or cyclic amide, opens its ring between the carbon and nitrogen, so it becomes an amide or ester. We call it as a ring opening polymerization reactions. You should have a ring, opens to become your polymer. Okay? Ring opening polymerization. Step growth and chain growth, I think I will describe a little bit more about this, as we start from. Okay. Traditionally, if you go back to your organic chemistry course or in your high school organic chemistry or chemistry course, perhaps you have known that the polymerization reaction may have addition polymers or condensation polymers and stuff like that. Okay? This condensation polymers, last time we talked about the Carrados. Carrados was the inventor of this polyester and nylon. Polyester and nylons are usually made by condensation polymerization reactions. That means that you have a byproduct. You have a byproduct, just like water or any alcohols and stuff like that. Okay? Addition polymers were very popular at the time in Europe during those 20s and 30s. Whereas the condensation polymerization reactions were very popular in North America, start with the Carrados to prove the Staudinger's macromolecular hypothesis. Okay? Well, addition polymerization reactions is something like this. We have a styrene monomer. Styrene has start from vinyl group. This is the vinyl. We call it as a vinyl group. And we have a substituent group or side chain is a benzene. Styrene. If you have an N number of moles of styrene, N number of moles, that means that you have many moles of styrene. One of this monomer was attacked by the catalyst so that your double bond will be open. It could be a radical, or it could be ions. It could be, depending upon the catalyst that you use. Okay? Therefore, we put this as a star. This star could be radical or ions. It could be anion or cation. So what we call this as active site. Anyway, if you have an active site from your double bond, but you still have a single bond, of course, covalent bond between the carbon and carbon, and this active site will react together between the molecules, so you form the another covalent bond between the this carbon and the other carbon from the styrene. So you have a growing chain. So we call this as addition polymerization reaction because we do not have any condensate. Okay. Methyl methacrylate looks something like this. So we have a polymethyl methacrylate. Let me describe to you how we can name this monomer. Okay. Now this is vinyl group, and if you have a carboxylic acid, what we call this is acrylic acid. Okay. When your carboxylic acid was esterified, in other words, if the acrylic acid was reacting with such as methanol or something, then this was replaced with the methoxy or methyl group in acrylic acid. We call this as acrylate, methacrylate. Excuse me. Remember that ATE and ig acid is how you name your carboxylic acid or ester, right? In your organic chemistry the textbook. So this is the methacrylate, MA, or abbreviated as acrylic acid. Now, this monomer, second monomer and third monomer, is a little bit different in terms of this hydrogen replaced with methyl group. Okay. Now, this is different from this monomer. Let me say this. Now, fourth monomer is different from this first monomer. First monomer, again, is acrylic acid, but this one is called methacrylic acid. Okay? This has a carboxylic acid, of course, but because of the methyl group in alpha position in the vinyl group, we call this a methacrylic acid. Now, when you esterify this methacrylic acid with the methyl group here, we call this as a methyl methacrylate. So this is the rule of how we can name the acrylate or related monomer products. Well, acrylic acid is water soluble, because of the presence of this carboxylic acid. When you polymerize this acrylic acid, then we call this the polyacrylic acid. Polyacrylic acid is water soluble, but if you cross-link a little bit, cross-link your acrylic acid, then you can make polyacrylic acid, cross-link the polyacrylic acid as a water-soluble polymer. Okay, it is widely used in your hygiene product for the ladies, okay, or it could be used as a 기저귀 뭐라 그러지? 기저귀. Such as a diapers, right? Diapers for the babies. So it absorbs a lot of water and sodium chloride solutions. The main product is coming from this polyacrylic acid. Okay? Water soluble because of the cross-linking reaction. If it's not cross-linked, of course it will be soluble in water. But you have to cross-link them to make it soluble. Okay? So last time we talked about linear polymer and cross-linked polymer. So cross-linked polymer is not soluble, but it's soluble. It absorbs the water, okay? But it's not dissolved in any organic solvent or water. So that's the difference between linear polymer versus the cross-linked or network polymer. So I said, you first make the linear polymer, but you have to cross-link a little bit to become soluble. Methacrylate is not water soluble because it's already, you know, the acidify your the acrylic acid. Methacrylate, however, is very sticky if you polymerize them. So polymethylacrylate is the main component of your Scotch tape. Okay, in the back of your Scotch tape, you have a very sticky adhesive. Okay, and if you polymerize them, this is the main product. I mean, polymethylacrylate. So it's quite different. Only difference is the methyl group here, but enormously, you know, your application is quite different. Polymethyl methacrylate, okay, polymethyl methacrylate. The difference between the methacrylate and methyl methacrylate is this one here. If you have a methyl group on top of this alpha position, then it's not sticky at all, but it's very hard plastic or glass-like the plastic. So it's very widely used as a polymethyl methacrylate is very widely used as a organic glass, or we call it as a the advertisement, the plastics. What they call in Korea is like a vinyl or acryl plate or something like that. It's very hard, sticky. It's not sticky, but it's very hard. Widely used as a advertisement plastics is the main component of this polymethyl methacrylate. Okay, so think about this: water soluble, sticky, and glassy. Okay, glassy and hard and rigid plastics. Polymethacrylic acid, it is not widely used, but it could be. You can make it. You can make an emulsion, or any of the other plastics as well. So anyway, depending upon just a little bit of modification in your monomer, your final product has a very different property. Okay? So we'll talk about the structure property of your polymer later on, but let's just think about the name of your monomers. Now, this monomer is the same as the third monomer here. And when you polymerize them, we can make just like a styrene cases, we can open this double bond, and it will be connecting to the alpha carbon and beta carbon is connected to each other. So we can make a polymethyl methacrylate, but because we do not have any condensate, this is called the addition polymerization reactions. Let's talk about the condensation polymerizations. Okay? Condensation, again, should have the byproduct. Okay? Let's see the byproducts here. Well, we have a diol. We should at least have two functional groups in your monomer. That's the essential part of or the requirement of making the polymer. So you should have at least two functional groups in your monomer. Okay? We have, in the case of ethylene glycol, we have two hydroxyl groups. So one hydroxyl group is called the one functional group. Because we have two hydroxyl groups, yes, this is bifunctional. And condensation reaction occurs between this hydroxyl. So we can make the polyethylene glycol. Polyethylene glycol, depending upon how many N that you have, it's water soluble. In the case of low molecular weight PEG, it's not water soluble if the molecular weight is very high. In the case of high molecular weight PEG, okay? So depending upon the molecular weight, it will be water soluble or not. Okay? Anyway, during this reaction, we have condensate, which is water. So that we call this as condensation polymerization. Okay? Now, let's think about this type of the monomer. You have a benzene ring, and when you have one carboxylic acid, okay, without this substituent groups, we call this as a benzoic acid. Okay? This benzoic acid was substituted with the hydroxymethyl group in para position, or 1, 2, 3, 4 position, so that this is what we call benzoic acid, but we have a 4 hydroxymethyl group substituted one. So this is the correct name of this monomer. Now, we have two functional groups. One hydroxyl, the other one is carboxylic acid. So carboxylic acid was attacked by the little basic hydroxyl oxygen. So there is condensation reactions in the presence of acid as a catalyst. Anyway, you have polyester. This is one type of polyester. Typically, I think you remember, polyester is coming from ethylene glycol reacting with terephthalic acid. So you should have two monomers in forming the polyester, like a PET, polyethylene terephthalate. But if you have one monomer containing two functional groups with different type, you can also make the polyester as well. So polyester is a typical name of the polymer containing ester functional group. Okay? So if you have an ester group in your polymer, we call it as a polyester, as a general name. Okay? Not only just a PET. So we have many types of actually polyesters. PET, PBT, PPT, many types of polyesters. Anyway, you have a condensate, so that polymerization is called the condensation reactions. One more thing that I would like to add here. Here, the arrow, look at this arrow. Arrow is always from left to right, okay? Left to right. If your arrow is from right to left, what happened? Now, arrow is coming from left to right, monomer to polymer. If the arrow is polymer to monomer, right to left, what happened? Degradation reaction, yes. you degrades your polymer to become small molecular weight components. So last time, I think the last part of our discussion, we talked about the degradation reaction, degradable polymers. Degradable polymers are the ones that come from right to left. So if your reaction is coming from right to left, you degrade your polymer. Okay? In biological system, in the photo degradation reaction, UV degradation reaction, chemical degradation reaction, you can make the degradable product. Okay? So now let's talk about again the polymerization reactions. Polymerization reaction should be performed from left to right. In order for your reaction to get the final product, you have to break the equilibrium of your reaction. In other words, your reaction is always from left to right, but you produce your byproduct. If your byproduct is remaining in your reactor, then there is always a driving force for the equilibriums. So the reaction is both left to right and right to left arrows. How we can break this equilibrium? Well, if you remove your byproduct from the reactor, then the reaction is coming from left to right. Okay? So you have to always remove your condensate to make your product as a polymer. So we will, of course, talk about in details. I think in chapter 4 or 5, we will talk about more. But I think, this is just an introduction, and I will not go in more details. But please remember about the equilibrium reactions in the case of condensation reactions. Let me ask you, this one. Styrene, is the styrene the bifunctional or monofunctional? Monofunctional? Correct? Well, we have one double bond. Yes, that's correct. One double bond. But double bond is regarded as a monofunctional? No, it's bifunctional. Because although we have one double bond will be cleaved, broken into two active species. Two active species. You see the two stars from, in both alpha carbon. We call this as alpha carbon and beta carbon, or carbon number 1 and carbon number 2. Alpha carbon to beta carbon. The double bond is cleaved into two active species, both in alpha and beta positions. So we call this as a bifunctional. So one double bond is regarded as bifunctional. If you have two double bonds in your monomer, we call that as a tetrafunctional. Remember that the last time we talked about the cross-link reaction. And when you would like to make a cross-link to polystyrene, we use a divinyl benzene. Divinyl benzene. In other words, we have one more vinyl group in here in the benzene, so we have two vinyl groups as a cross-linker. And in that case, this divinyl benzene is acted as a cross-linker because we have a tetrafunctional monomer in that system. Okay. Another example is, let's say, now this is a polyester. Okay. In this polymer, we have the carbonyl and ether connected to each other, so we call this as a polyester as well. This is also polyester as a final product. Of course, we have N, but the starting monomer is different. We have both carboxylic hydroxy acid as a monomer, which was very typically used as before. So we have a byproduct here, byproduct. This reaction is called condensation reactions to make a polyester. But polyester can be prepared by the addition polymerization reactions without any byproduct in the case of ring opening polymerization reactions. Okay? We have a cyclolactone. This is called the cyclolactone, or the omega hydroxy, the carboxylic acid. So you can make the same product from the two different monomer, from two different, the reaction polymerization reactions. We can make the nylons as well, polyamide, from the same reactions. We can have amino acid, or we can have a cyclolactam, lactam. Okay? First one is addition polymerization reaction, and the second one is called the condensation polymerization reactions. But both of them are step growth polymerization reactions, not chain growth, but step growth. Step growth, but addition and condensation. Step growth, addition and condensation reactions. Okay? Have you heard about the polyurethane? Urethane? Polyurethane. Polyurethane is very widely used in the rubber or the synthetic leather. Well, what the in Korea we call it as a leja라고 하나? leja. Well, the covering fabric or the leather in your sofa or the chair, or the synthetic, the coat is made from polyurethane. And most of the ladies in Korea are wearing the so-called 쫄바지, okay, are all made from polyurethane, in fact. Okay? So polyurethane can be used, of course, also we have a shoe sole. This back shoe sole is made of polyurethanes as well. So in some cases, the polyurethane is quite flexible. In some cases, it's quite hard. Okay? It's very hard. It should be hard. Now, polyurethane have the structure with this one here. Okay? We have NH and CO and O. Now, COO is called ester. NH and CO is called amide. And we have, this is a combination of amide with ether, or NH versus the connecting with the ester. So NH and COO is called urethane linkages, urethane functional group. Now, urethane functional group can be made by both addition polymerization and condensation polymerization reactions. In the case of condensation polymerization, we have a diamine, okay, and acid chloride. So this amine will attack this carbonyl. So you have a HCl coming from one of these, the two monomers. So they have a byproduct here. The same product can be obtained from dihydroxyl versus the diisocyanate. This diisocyanate is very reactive. If you have a hydroxyl, hydroxyl will attack this carbonyl and opens this ring, so that you have a rearrangement of a hydrogen or proton attacking over here. So you form the NH and COO without any condensate. This isocyanate is very typically appeared in your IL spectrum at around 2200 reciprocal centimeter. hydroxyl appears around the 3300 reciprocal centimeter in your IL spectrum. But after reaction, if it becomes urethane, okay, there is no peak in this characteristic, the urethane bond, but we have a 15, perhaps 50 reciprocal centimeter, and this carbonyl appears around the 17, I think 17, 15 in this ester cases. So before and after reaction, if you check your IL, when the product do not have any, isocyanate and hydroxyl and appears this characteristic peak, then you confirm this reaction is complete. If you still remain some amount of this isocyanate after reaction, then you should remove your isocyanate later on anyway. So by looking at these IL peaks of your before and after reaction, you can confirm your reaction, polymerization reactions. The isocyanate is very reactive with the water or with the hydroxyl groups, or with the water even in your the air. Okay, so you have to keep your isocyanate in a very dry conditions. Otherwise, this isocyanate will be completely gone. Now, depending upon what kind of aliphatic group, or depending upon whether you have aromatic ring in between the isocyanate, you can make a very hard material, hard urethane, or soft urethane. Okay? Hard urethane is coming from the presence of aromatic ring. If you have benzene ring between the isocyanates, you can make a very hard polyurethane. If you have if you wanted to have a flexible, leather or Jolbaji type of polyurethanes, then you need to have aliphatic chains between isocyanates. Okay? So for example, I think this one will be quite flexible. But if you have aromatic rings, benzene rings between these urethane bonds, then you can make a pretty hard and rigid polyurethanes as well. Again, the first one is addition polymerization reaction, and the second one is the condensation polymerization reactions. And again, in order for the polymer to be formed, you have to remove this HCl byproduct to proceed your reaction from left to right. Okay? You can make a polyethylene. Usually the first reaction is quite typical. You have ethylene monomer. You add your initiator to make the polyethylene. Now this reaction is addition reaction. The second reaction is called the condensation reactions, but condensation reaction is not very typical to make this the polyethylene. But the first addition reaction is quite widely used. Okay? And in this case, the first reaction is quite, the addition reaction is pretty typical and traditional. But this one is called the condensation reaction. The Stackless polymerization reaction, but addition reaction and condensation. This is the chain-cross polymerization reaction and addition reactions. This is the condensation reaction and Stepwise Polymerization reactions. Okay? So if you go back to the first slide, addition, let me summarize this. So we have talked about the step growth and chain growth. In the case of step growth polymerization, usually step growth was regarded as a condensation polymerization reactions, or you have a byproduct such as the water. In the case of step growth polymerization, we also have addition polymerization reactions without any byproduct, such as the case in the polyurethanes. In this case, we could have a polyester or polyamide, and so on. In the case of chain growth polymerization reaction, the typical reaction is addition reactions. Perhaps we do not have any condensation. Typical reaction is a polyethylene, polypropylene, polystyrene, stuff like that. Now, finally, we can talk about the ring opening polymerization reactions. We already saw the ring opening polymerization cases. For example, polymerization of lactone or lactam. We also have polyether here. It could be, polymerized to become a polyethylene glycol. Excuse me, polymethylene glycol, or polyether, or you can make a. This has already been explored. We can come from the lactam, or excuse me, the lactam to become nylon 6. We have epoxy to become polyether. Okay, epoxy ring. I think you have heard about the epoxy adhesives or resins can be made from this reaction, and so on. So in summary, step growth polymerization and chain growth polymerization are a little bit different. The step growth polymerization reaction, usually the molecular weight is quite low at the beginning, but pretty high later on. Whereas in the case of chain growth polymerization reactions, molecular weight is pretty high at the beginning. You start from very high molecular weight. So that's the difference between this step and the chain growth polymerization reactions. We do not need any initiator here, but we used to have need the initiator. Okay? In the case of chain growth polymerization reactions, there are very important 3 steps, elementary steps. Initiation, propagation, and termination reactions are quite required in the case of chain growth polymerization reactions. But in step growth, we do not need that type of initiation, propagation, terminations. So there are no terminations. I think we'll see how the step growth polymerization reactions will proceed. Okay? Now, let's say that we have about 25 monomers. We have 25 monomer as a dot. Okay? Let's say that we have 25 monomers, 5 and 5, just like your Go, Baduk Go. Step growth polymerization proceeds from any monomeric units between the two, or between 2 functional groups. So it could be from here. So we have a 25 monomer. Let's say the reaction proceeds something like this. So we have let's count how many molecules here? Tell me, how many molecules? Could be 12 or 13, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So starting from 25, we come up with 13. So half of your monomer, half of your molecule participate in the reaction. So just counting the number of molecules, 50% of your reaction was already completed. Okay. Now, for some monomer, can be connected together just like this. So later, a little bit later, how many molecules do you have here? 6, 7, 7. So about half of them were already completed. So you can say that about 75% of your reaction was proceeded as well. So number of molecule is quite important to determine your yield and to determine your conversion percentages, right? So the Stackless polymerization reaction proceeds something like this. Any monomer can participate in the reaction. Any molecule can participate in the reaction in this case. So we can count the number of molecules during the reactions. However, in the case of Carrados polymerization reactions, reaction proceeds something like this. Okay? It's like a chain reaction. It's like a Lego block, breaking down onto here. So one monomer starts to proceed the reaction to the next monomer and next monomer. You have starting from 25 monomer. We have about 12. Let's say we have 13 molecules here. So by just counting the number of molecules, we have a same 50% reaction was proceeded as well. But the reaction procedure is quite different. Molecular weight, in this case, is a trimer, dimer, monomer. So molecular weight could be just, average is about 2 degrees of polymerization or 2 repeating units. However, we have about 13, in this case, repeating units, whereas we have a smaller one. So we have a pretty wide molecular weight distribution. In some cases, we have a pretty high, 13 repeating units. In this case, in this molecule, we have about 19 degree of polymerization. So molecular weight is pretty high at the beginning in this case, whereas molecular weight is quite low at the beginning, but of course it will become high later on. So it takes some time to increase your molecular weight, whereas molecular weight is pretty high at the beginning. Okay? So these are the difference between the step growth and the chain growth polymerization reactions. So if you go back to this slide, I think we can talk about difference between the molecular weights. Monomer consumption was quite rapid here in step growth, whereas in the chain growth, the monomer consumption is quite relatively slow. Initiator is not necessary here in this case. Initiator is quite essential in the case of chain growth. Termination, polymerization rate decreases, polymerization rate increases initially. So those are the differences between step and the chain growth polymerization reactions. Okay. But in more recent years, we need to talk about the step and chain growth and classify this into the step reaction and the polymerization reactions rather than addition and the condensation reactions. Step growth reaction, We have two types of Stackless polymerization reactions. The first one is bifunctional in one monomer, just like a hydroxy acid. Okay. A and B represent each functional groups. Okay. So you have two functional groups in one monomer, just like amino acid. You can proceed with the reaction, can become a polymer. AA and BB are, for example, ethylene glycol and terephthalic acid, okay, reacting together to become AA and BB type of the condensation polymerization or Stackless polymerization product. Okay. You can make both of these cases to become a polymer. So the reactive functional groups could be in one monomer, or it could be two different monomers. So esterification reaction is a very typical example of this Stackless polymerization reactions. In these Stackless polymerization reactions, we have to realize the very important Carrados equation. Okay? Carrados equation. Carrados equation is not very difficult. I think you have already done your kinetic course, or physical chemistry, or the reaction engineering courses. If you have already taken that, I think it's very simple, but a little bit of different definition, or perhaps the terminology might be a little bit different, but exactly the same. So let's say we have, let's say that N and N0, okay? N0 is the initial number of molecules, just like a 25 molecules that we have. You have a 25 spots, right? You have a 25 is like N0. N is 13 or 7, something like that. So N could be representing the molecules, number of molecules at a given time t. At some time later, like 1 hour or 30 minutes later at time t, after time t, you count how many molecules in the reactor. It's called the large N. And let's say that N0 minus N, okay? The initial number of 25 minus N, which was total molecules 13. Then it's the how many molecules were remained in your, how many molecules were consumed or reacted, okay, right? N0 minus N is the number of molecules that was consumed during the reaction. Let's define the conversion percentages. Conversion means you can also express that in terms of the how many molecules that was consumed divided by the initial number of molecules. Okay. Let's say N0 is 25 here. N0 minus N is like a 12. Okay? So P is about 0.5. About 50% of your reaction was proceeded, whereas can be calculated from this equation. Right? 75% of your reaction was proceeded here at 0.75, 25 here, and it could I think this was what 25 minus 7 in the case of 75% reactions. So it's very simple. And definition of N, which is the one that was total number of molecules at a given time t, can be calculated if you know about the conversion, if you know about the yield, okay? Right? So it's very simple. You can replace this with the C. In the physical chemistry course, you call the C concentration of your molecule or any reagent at a given time t after reaction is equal to C0 times 1 minus P, right? It's exactly the same. N is equal to N0 minus, times 1 minus P. Now, let's say the degree of polymerization. Let's define the degree of polymerization. Degree of polymerization, according to Carrados, was just very simple. Initial number of molecules divided by the number of molecules at a given time t. It's defined as a degree of polymerization. So dP is just number of molecules in the residue, but if you know the initial number of molecules and the number of molecules at a given time t, you can calculate n, or dP. If you, because of definition here, n is equal to n0 times 1 minus p, if you replace this, n with n0 times 1 minus p, then you can cancel this out to become 1 over 1 minus p. So dPn, according to Carrados, is 1 over 1 minus p. So if you know the conversion, in other words, how many percent of your the molecules will participate in the polymerization reactions, you can calculate the degree of polymerization reactions. You can calculate how many, reaction was proceeded to. This is the Carrados equation. So he published an article in Journal of American Chemical Society in 1929 that says that you have to have a bifunctional group or higher functional group in order to become a polymerization to be proceeded. It's a very simple statement, but was very sensational and very important. So it was published along with this equation at the time in 1929. So let's say that we have about 80% conversion. So 80% conversion means P is equal to 0.8, right? Now, let's say we have about 10 molecules right here. 10 molecules, so N0 is equal to 10. If you proceed with the polymerization reactions, later we have 2 molecules, right? Starting from 10 molecules at a given time t, N is equal to 2, okay? So you can replace this N0 and N here, so you can calculate the degree of polymerization reactions. So dP here in this case could be 5 here, because N0 is about 10, N is equal to 2, so you can determine dP, which is 5. Or if you know P, 80% conversion, which is 0.8, so 1 divided by 0.2 is 5. So it's exactly the same. So you can simply calculate dP if you know how many molecules at the beginning and at a given time t, or the percent conversion. You can determine very easily N0, because N0 is the one that you can determine, because you weight your moles of your monomer at the beginning. So N0 is very simply determined by yourself. But N is quite difficult to know, okay? Difficult to know, but there are some ways of making or determining this N. So determination of N or measurement of N is the critical factor, but the N0 is not a problem. Okay? In typical cases, what they do is very simply, after reaction, you just take the small portion of your the product at a given time t, and in the case of a functional group, this might have a functional groups at the end, right? So if you determine the terminal group by titration, okay, then you will determine how many moles of your hydroxyl, for example, or how many moles of your carboxylic acid, how many moles of your amine groups. Then you will know how many moles of your, in this case we have 4 functional groups instead of 20 functional groups. Okay? So if you know the moles of your functional groups left or remained at a given time t, then you can determine number of molecules. Okay? In chain-cross polymerization reactions, in the case of chain-cross polymerization reactions, I told you that we have three very important steps, right? Initiation, propagation, and termination reactions. Initiation, propagation, and termination reactions. I think you can take a look at the chapter 8 of your organic chemistry course. You can take a look at those these steps. Initiation. In the case of ethylene monomer, if you have a radical, for example, once you've generated radical, all dot means that you have electrons. So electron, radical, right, will attack this double bond. So double bond will be cleaved into two radicals. So one of these radical from the one carbon will combine together to become the covalent bond, and the second radical is remaining at the end, okay, at the initial stages. So initiation means that you have one radical in the left-hand side and another one radical in the product side as well. So you have both radicals in the left and right. Propagation means that the radical, preceding radical, will attack this monomer. So you have a growing chain, one radical here in the left-hand side and right, the other one in the right-hand side as well. This is quite proceeded consecutively and repeatedly to become a final product of your growing chain. So propagation step is a determining step to make your high molecular weight components. So both addition and ring opening polymerization, the reaction propagates at a reactive chain end, and continues until the termination reaction occurs. Okay? So initiation, propagation has both radicals in the left and right-hand side. Okay? However, in the termination steps, this growing chain in the two growing chain will meet each other to make the final product by combination. This is what we call the combination. Combination means that two growing radical will combine together. Okay, combine together, so molecular weight will be doubled. Okay, molecular weight will be doubled in the case of combination termination reactions. Or we have a disproportionation reaction, meaning that one growing chain will terminate so that the molecular weight is just one. It's not double, but it's just one. It could be backbiting, it could be disproportionation, which we will talk later on in more details. Okay. Anyway, the termination reaction is the one that chain terminates, so your radical will disappear. So there is no further active sites to proceed for your chain-cross polymerization reactions. Okay, so these were a brief introduction of today. I think we have talked about what type of polymerization reaction is actually present, and in summary, I think we have talked about the Stackless and chain-cross polymerization reaction, and addition and condensation reactions. Okay. This is just a brief summary, and I think we will talk in more details about the step growth for I think about 3 weeks, and chain growth for about another 3 weeks in more details. And this is just the introduction. Okay. I hope that you can see the nomenclature of these polymers. Okay. Nomenclatures were listed in the back side of your textbook, and we can just copy this here. If you know the name of the monomer, then you will be able to name your polymer. Okay, just like what I have described in the case of acrylic acid and or the methacrylic acid and so on. So for example, this monomer, the first monomer is called the propylene. We have a double bond, and side chain is methyl group here. And when you polymerize them, you can just put polypropylene. Okay? So monomer structure information, monomeric structure information is very important to name your polymer. Okay? Isobutylene, polyisobutylene, stuff like that. So if I will look at this second monomer is called the polyvinyl chloride. This is propylene, so we call this as a polypropylene. This is isobutylene. So polyisobutylene is the name of this monomer. Polyisobutylene can be used as a little rubbery stuff. So that I think these days this is very widely used by mixing the starch or natural polymer with the polyisobutylene, you can make several biomedical products to touch with your skins. In Korean words, I think you can put on top of your skin for the ladies. I think if you have any small surgery on the skin, your body will explore your natural water to protect your contamination of your skin. Then you put something on top of it, like a skin product, and the polyisobutylene is very widely used in that the biomedical product. Polyacrylonitrile has a CN group here in place of Cl or methyl group. CN again has a dipole moment. Okay, C triple bond N. So, between this N and C, you may have a dipole-dipole interaction. So dipole-dipole interaction will make your polyacrylonitrile very crystalline. So you can make the crystalline, semi-crystalline acrylic fiber out of this polyacrylonitrile. Methyl methacrylate is very rigid one because of the presence of a methyl group in the methacrylic acid here. Your glass transition temperature will be much increased if you put the methyl group, which is non-rotatable. The CC group here in the backbone is not rotatable by the presence of this methyl group, which blocks the rotation. Therefore, this polymer will be quite rigid, so they can make glassy, advertisement acrylic the plates. Vinyl acetate is the one that you have a vinyl group over here, but your position of COO is a little different. Okay, in this case is COO. This OCO is the difference. You start from vinyl alcohol, and you esterifize with the acetic acid. So this is called the vinyl acetate. Vinyl pyridine is water soluble. Isoprene is a natural rubber, and chloroprene is synthetic rubber as well. Ethylene oxide, polyethylene oxide, polyethylene glycol, formaldehyde, acetaldehyde, and stuff like that. Those were very important products. This is the PET, polyethylene terephthalate. Okay. Caprolactam is becoming a nylon 6. Nylon, the number after this nylon represents how many carbon number of molecules in your total the brackets, repeating units. For example, in this case, we have C5 and C in the carbonyl, so we have 6 total carbon in the brackets in repeating units. We call this as a nylon 6. If you have 11 or 10 number of methylene units, we call this a nylon 11. 610 means that we have 6 in the diamine and 10 in the 8 in the diacid group here, plus 2 carbonyl will become nylon 610. This is the Nomex type of the polymer. This is not Nomex actually, but we have a Kevlar is the one that you have a para position 1. And if this is the para positioned here, then it will become, yellow fabric, okay, yellow fabric, which did not burn. I think I lost the box from Wednesday. So if anybody saw those box, please let me know. Okay, so the name of this product is quite important, and perhaps later on I think we can have a quiz on this name of the polymers. So please remember every time that you mark the name of the polymers. Okay? I can show you the monomer, and please make the polymer. I will give you the chemical structure and you name the polymer, or if I will name your polymer, then you need to write your chemical structure with the polymers. Okay? Okay, with that, then I think we can continue our discussion. In chapter 3, about the property of the polymers, we will upload the chapter 3 in PDF file so that you can take a look at it, and we can come back on next Wednesday and discuss about the properties. Okay, thank you, and I'll see you.